Welcome back, everyone. Today we're going to talk about floating point numbers. I'm going to assume that you've already had an introduction to it. However, you want to review it and you want to shed some light to some of the aspects of it that may have been mysterious to you. Let's dive into it. So I'm going to talk about single precision floating point numbers. Now we know that single precision it has 32 bits, and the first bit is the sign bit. If it is a 0, it's a positive number. If it's a 1, it's a negative number. The next 8 bits are the exponent bits, and the other 23 bits are called the fraction or the mantissa bits. And here it is. We can see it. This is either called fraction or mantissa, depending on the book or your professor. Next up, we should know that binary values for the floating point representation are unsigned. What that means is that when we have, let's say 1, 1, 1, this would be, if it was signed, this would be -1. But because it's unsigned, this is going to be, let's remember how we do it, 1, 2, 4. So all of those are set. That would be 7. So we're going to think of this as 7 and not -1. So they are unsigned. All of those values that we utilize, all of those values that we have, they are all unsigned binary values. All right, so the next thing to know is that the exponent is biased by 127. And I'm not going to go too deep into that, but just know that this simplifies hardware implementation, provides us higher range of exponents, helps us, gives us the normal numbers, and more. I'm going to talk about normalized versus denormalized, and we'll see what the differences are. Now let's do an example. All right, let's say we have this floating point representation of some number. These are the bits. The first one is the sign bit, so that tells us that this is a positive number. So we could just write them down. Let's say sign. The sign is positive. Now let's go with the exponent. I'm just going to say exponent. So the exponent is this portion right here. Now, what does that come down to? So we know that when we have 8 bits, the very first bit is going to be, so that's going to be 128, right? And this one is also flipped, the first index. So that's going to be 1. Now we know that that is 129. All right, that is 129. Now we need to subtract the bias, which is 127. That would give us 2. Now we know that the exponent is 2. We know the sign is positive. Now let's go with the fraction. All right, so we should know that when the number is normalized, there is an implicit 1 in front of the. There's an implicit 1 in front of the fraction. So it's going to be 1 and then followed by these numbers. So it's 1.1011. I'm going to explain why that is, but just trust me that we need this 1 in here. This is an implicit 1 there because this is a normalized number. We're going to talk about how we can tell that this is normalized and that we do need the 1 in there. So right now we can see that this is the fractional part, and this other value right over here, the 1 is just the implicit 1. Implicit. That's just always assumed to be there. So not always. I'm sorry. It's assumed to be there if the floating point representation is normalized. Now, how do we know that something is normalized? If the representation is normalized, let's go further. Well, actually, let's complete the calculation first. But we'll talk about how to tell if it's normalized, if we need that 1, or if we need a 0 in front of in its place. So let's continue with the calculation. So we got our fraction to be 1.1011. That is our fraction. Now, we also know that our exponent is, all right, times 2 to the power of 2. This 2 right here is our exponent, right over here. That is the exponent that we have. Now, what would this be? We need to shift the bits. Let's actually do that over here. Now, we know that this is a scientific notation just for binary numbers. So that would just do 110.11. What we did, we basically said shift the numbers twice and the decimal point twice, because we have that number over here. We have 2 to the power of 2. It's pretty much the same as scientific notation, just for binary numbers. So this is our number now. This is our binary number. Now we need to treat these the numbers to the left of the decimal point differently from the numbers that are right of it. The ones to the left are going to be just simple unsigned binary numbers. So what is this really? Let's talk about it. So let's say this is what we have for the digits place. So that would be 1, 2, 4. All right. So if those are ticked, then we have a 6, right? That's 4 plus 2. That is a 6. Now that is this portion in here. That is let me get the appropriate color. This is that portion in there. And for the fractional part, we have, what do we have? We have 1 and 1. However, in this case, it's not going to be the same calculation. In this case, it's going to be 1 over 2, 1 over 2 to the power of 2, or you could just also say 1 over 4, 1 over 8, and it just keeps on going. The other one would be 1 over 16, if I'm not mistaken. So now, what do we have here? We can see that from after there, it's all zeros, right? We don't need to. That's why we didn't write it down. If I wasn't clear, let me show you. So over here, we only took 1, 0, 1, 1. The reason why we did that, because we don't care about the zeros that come after you. So there's a bunch of zeros. It doesn't matter what these other values are. 1 over 8, 1 over 16, it doesn't matter. We're going to ignore that, and we're going to continue with this. So now we know what's going on over here. So it is 1 and 1. So it is 1 over 2 plus 1 over 4. In the numbers case, in this case over here, we just said 4 plus 2, but in this case, we're just saying 1 over 2 plus 1 over 4. Now, what would that give us? We can put this into the calculator and get that value easily. I think if we do 2 times 2, that's 4, plus that's 3 over 4. Now, if we put that through the calculator, I think we're going to get 0.75. Now, what we know is that our calculation, our final result is 6 plus 0.75, which is 6.75. That is our final result. This is in decimal. I'm going to put the subscript so we can tell. And that is pretty much it. The way we did the calculation, we said, let's first check for the exponent. What is the exponent? The sign. I'm sorry. The sign. So the sign is positive if it's 0. If it was 1 over here, we would have the sign to be a negative number. The sign would be negative. For the exponent, we just calculated the unsigned value. we treat everything as unsigned, and we calculate it. So we had 129. We then subtracted the bias, so we got 2. That meant we are going to have this business over here. We also added the implicit 1 because we know that this is a normalized number. I'm going to talk about how to tell if something is normalized or not. It's coming soon in this video. So normalized number, so we add 1 in front of the fraction, where there's this implicit 1 in front of the fraction. So then multiply by 2 to the power of our exponent. This 2 is always here, this one, but the exponent is something that we calculated. All right, so then we split them into different parts. Right over here, we can see we treat the binary bits to the left of the fraction point differently. We treat them as just unsigned binary numbers. For the ones that are to the right of it, we are doing a different calculation. We're saying 1 over 2 plus 1 over 4, and these values, as you can tell, it is just 2 to the power of, it's 1, then 1 over 2 to the power of 2. If you want to get them to the power of 3, that's pretty much what it is. And something to note is that it starts with 1. It starts with 1. It doesn't start with 0. That is very important because sometimes you can get the incorrect result if you're not careful. With this, it actually starts with 0, because what we're really saying is we're saying 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. That's where we get it. We're getting the numbers of. What was it? It was 1, 2, and 4. That's what we're getting those numbers from. So but in the other case, for the fractional portion of it, we only have 2 to the power of 1. 1 over 2 to the power of 1. All right, that is something to keep in mind. Now let's go down. No, there's this important thing, as we talked about, normalized versus denormalized. What is normalized? So how to tell? So the way you can tell if a number is normalized is that it will not have all zeros or all ones in the exponent field. So let's go up. So if all of this exponent field, if all of those numbers were ones, a bunch of ones, or a bunch of zeros, all zeros, then in that case, we would know that this is not a normalized number. In our case, we have variation, so it's 1, 0, a bunch of zeros, and another 1. There's variation, so this is a normalized number. That is how you can tell. It might be a little backwards the way I've written it, but it's fine. You can write, you can take notes, you can write it in your own words, you can make it easier for yourself. The way I remember it is that if it's a normalized floating point representation, it will not have all ones or all zeros in the exponent field. Now, and if that is the case, there's an implicit 1 that we add in front of the fraction. So for denormalized, the denormalized representation will have all zeros for the exponent. So the denormalized is going to have all zeros right here. All of these are zeros, not ones, all zeros. That will be the denormalized representation. And if we have that, there's going to be an implicit 0 in front of the fraction. Right here we have a 1, right? But instead of that 1, it would be a 0 if we had all zeros in the exponent field. Now let's go down. All right. So there's a few important things that I've written down that will help us out. When the exponent is all ones and the fraction is all zeros, this will denote negative and positive infinity. Of course, the sign bit can vary. That is how it works. So if we have, let's write it down real quick over here. So if we have, let's say, positive, and the exponent is all ones, so if we have all ones in the exponent field, that is 8 bits of ones, and the fraction is all zeros, this is going to be the negative infinity, right? Negative infinity. And likewise, if this was a 0, this would be positive infinity. All right, I'm going to clear that out. So the next thing is when both exponent and fraction are all zeros, this denotes positive and negative zeros. And of course, a lot of the times there's no difference between positive and negative zeros. However, some calculations require us to show when values are coming increasingly close to positive zero and negative zero, but it sometimes, most of the time we don't really care about it, but some calculations do require that. So keep in mind that this is what it's used for. The next thing is that when exponent is all ones while a fraction is not all zeros, this is not a number. Let me actually show you what that means. So the sign could be anything. The exponent is all ones, so 8 bits of ones, and the fraction is not all zeros. So the fraction would have some value like that. In this case, this is not a number. This is used to denote numbers that are not possible. For example, if we had 1 divided by 0, this would be not a number, and that's how you would pretty much show it. So if there's some calculation that results in something like this, it would denote not a number. All right, and let's see. All right, so I have an example over here of this is a decimal value, negative 5.25. We're going to convert that to floating point representation. Now, how are we going to do that? All right, let's see. Let's write down everything that we need for the chart. The sign bit, the exponent bit, and the fraction, frac. All right, so we know that the sign is 0, so that's going to be 1. I mean, the sign is negative. I can't talk today. Right, so if the sign is negative, it is 1. Beautiful. Now we are going to calculate the exponent and the fraction. At the moment, we don't have either of those things. So I'm going to put the value to the left of the decimal point here, and the value to the right of it over here. We're going to calculate the binary representation for both of those things, and then we're going to put it through the whole process. Well, divided by 2, what is it? It's going to be 2 with a remainder of 1. All right, now we have 2 divided by 2. We have 1, a remainder of 0, and, all right, 1 divided by 2 equal to 0 with a remainder of 1, correct? And after that, we don't have, well, we could also say, 0 divided by 2, but it's not going to give us anything important, so we're going to ignore that. So what this is giving us, we're going to remember when we're dividing, we're going to read the binary bits from bottom to top. So that's going to be for us, and that's 1, 0, 1. Now let's try to understand what that means. This is an unsigned number. Remember, all of these are unsigned. So it's 1, 2, 4. So that is basically 4 plus 1. And that's 5. All right, that sounds correct for us. So we're going to let that be there. Now let's try to deal with the 0.25. All right, I forgot to put the point. All right, so 0.25, we're going to multiply that by 2. We're going to say that's equal to 0.50. I'm going to say remainder, but it's not a remainder, but you can just treat it as such. Whenever this digit over here, the number to the left of the decimal point is 0, you're just gonna say remainder is 0. That's all. If there is a 1, we would put 1 in the remainder. It's not technically a remainder, but it's just something you can treat as such to help you calculate these results. 0.5 times 2 is going to be 1.0. Now our remainder is 1. It's not a remainder again, but it's just something to help us denote. You could just call it a D for digit or whatever you want to call it. That is just something that helps us to make these calculations. All right, so now every time you go down, notice when there's a 1 over here, we're going to subtract 1 from it. When that number is greater than or equal to 1, we're subtracting 1 to it. So the next value is just going to be 0 times 2, which is just 0. So, we don't care about it. We could just write 0, but it doesn't really matter. Now, let's notice something. We are multiplying in this case, right? Let me just have a separator over here so we don't accidentally do anything wrong. All right, so we are multiplying, right? So in that case, we should remember that we're going to read the values from top to bottom. And in this case, we have 0, 1, 0. For the other guy, we had 1, 0, 1. All right, beautiful. Now we're going to put these together. It's going to be 101.010. So now what would you do in this case? Well, I think what I would do is I would say 1. This is what we need to get to, right? So this is what we want to represent it as. Now we need to multiply something to it so that the value is actually correct. What would you do? So we need to do times 2 to the power of some value. In this case, we can see that we moved the decimal point twice, so it is going to be 2 to the power of 2, and this is what we have. So let's go back to our thing right here. I'm going to move it down. We know that the sign is 1. We know that the exponent, well, at the moment, right here, we have 2. However, remember that there's the bias, so we need to say 2 plus 127, right? And this is going to give us 129. The fractional point is going to be this portion right here. All of this. We are going to exclude the the 1 in front of it because it is implied that it's already there. It is an implicit value for our normalized floating point representation. 0, 0, 1, 0, 1, and 0. That is our fraction. Now to represent it with the IEEE representation, for the floating point, single precision value representation, it would be, let's just have a small chart over here. So it's going to be the sign. This is going to be the exponent, and the rest will be the mantissa, or the fraction. So for the sign, we know it's 1. For the exponent, well, let's convert this into binary. So that would just be 1, 0, 0, 0, and 0, 0, 0, 1. Because we know this is 128. This is just another 1. That'll be 129. So that is our value. We could just copy that over. Copy that over here. All right, beautiful. And the other portion is going to be our fraction, which is 0, 1, 0, 1, 0. And there's a bunch of zeros here, so that's why it didn't really matter to include that 0, but it's fine. All right, we can see there's a bunch of zeros. The number over here has to be 23. So since we already have 4 of those, it's going to be 19 zeros. I'm not going to put all of them to save time, but it doesn't matter for us. All right, so this is the sign. This is the, the exponent. This is the fraction, or the mantissa. All right, now let's do another example. So let's write these down. Sign, the sign is 0 because it's positive. Exponent, fraction. Beautiful. Now, let's see that our number is 0.25. So we don't have digits to the left of the decimal point. So we're just going to calculate for the fractional point. And it's 0.25 times 2 is equal to 0.50. The remainder is 0. Again, that's not a remainder. It's just something that I use to help me make sense of it. So this is just 0.0, and that's going to be 1 when this number is 1. The next thing is just going to be 0 times 2, because we're saying 1 minus, no, this value, basically minus 1, and then we do that. So this doesn't matter. We're not going to write that anymore. Let's remember that for this one, we just go from, top to bottom when we read these bits. Go from top to bottom, so that's just going to be 0, 1. All right, that's what we have. And now let's remember that the number from to the left of the decimal point is just 0. So if you just do 0 divided by 0, 2 is going to be 0. The remainder is also 0. So, the actual thing that we have, and we remember to read it from bottom to top, is just a 0. So our actual value in the end is going to be this number. And now, since we have this value, we're going to try to have that be represented with an implicit 1 in front of it and all the zeros over there. How would we do that? Well, let's think about that. Let's first write it down. 1.00. It doesn't matter how many zeros you put in there, but just for the sake of understanding. Now, let's see. What would you multiply to this? Multiply 2 to the power of what would it bring it back to this? Because essentially we're trying to represent this same thing, because essentially we're trying to represent this in scientific notation. Remember, when we have in the decimal form, we have, let's say, 4.0 times 10, that's going to be 40, right? 40.0. And if we did 4.0 times 10 to the power of negative 1, that would essentially be 4.1 times 1 over 10 equals to, well, that would be 0.4, right? Because we're dividing by 10, that's going to go that way. Now we're trying to multiply, this number by 2 to the power of something, so that when that calculation is done, it actually looks exactly this one. So we're trying to represent the same number. However, in this case, we wanna have this to be in scientific notation for the binary number. So what would it be? We're trying to, because let's see, we moved this decimal point twice, right? And we want to go back. We moved it twice to the right. We want to go back, so that would be negative 2, right? That was twice, so it's negative 2. It is the same idea with the decimal, just for binary numbers. You just look at the value, you try to understand what would you multiply to it, so to make these guys be the same value but in different notation. All right, so now we have our exponent. So that would be negative 2 plus 127, our bias. Now would be 125. Now the fractional part, we can see that. All right, this is the fractional part. It's all zeros, so it's a bunch of zeros. You can just put a bunch of zeros, 23 zeros, right? And now let's do our chart. All right, the chart is going to be, so the first is 0 for the exponent, and we need to calculate this for the bit, for the exponent bit, right? So that would be 0, 1, 1, 1, 1, 1, 0, 1. And you can watch the videos earlier that I've posted to figure out how to do that, how to do those calculations. All right, and here that's just a bunch of zeros, 23 zeros. So this is the sign bit, exponent, and the fraction or the mantissa portion. All right, pretty much we are done with that one. Now let's think about why we were able to basically convert this to that and have it be a normalized function. You see that one over here, the one that we have over here, it wouldn't have worked if it would have been a 0 if this was a denormalized number. Now, the reason why we're able to do this is because this number is just, we were able to represent it in the normalized form. However, if this number is very small, if that number is very small, let's say that number was 0.0000, like a very small number, and that's like 25 over here, like whatever value you want. There's just a bunch of zeros that goes on and on. In that case, we might not have that. We will not be able to represent it with the same strategy because the the exponent value has a limited range. So instead of that, we use denormalized numbers. Now let's briefly talk about the denormalized numbers. I don't think this is going to be in the exam because this is kind of difficult. But one thing that might be there is a representation in the floating point, a binary bit, a string of binary bits that you might have to convert from floating point to decimal. Now, let's just say we have this number. I'm not going to write it in terms of decimals because this is such a small number that it's difficult for me to show it in terms of decimal. Just know that since the range of our exponent is limited, we can't represent everything using normalized numbers. So let's see what this is. So we know, since this is a hexadecimal, for 8 that would be 1 0 0 0. For 0, it's just a bunch of zeros. And for the 6, we have, that would be 0 1 1 0. And this follows with a bunch of zeros until we have 32 bits for the single precision. So now we know that we can have our chart. So that's for the sign bit. So let me show. This is the sign. This is going to be the exponent. All of that, because 8 bits. So 0 0 0 0 and 4 more zeros. That is correct. All right. So for the fraction or the mantissa, we have 1 1 0 0 0. Now this number is quite small. If you try to put it through a converter online, or maybe a calculator, to a decimal, you would see that this is a very small number. Now, and there's a bunch of zeros all the way. So we notice that the exponent is all zeros. Remember, this is the denormalized structure. So since we have the sign bit, let's actually write it down. Sign. The sign bit is 1. So that means it's a negative. It's negative. And the exponent, we can see it's all zeros. In this case, what we do is we say 1 minus 1 2 7. Because when we have all zeros, we interpret that as 1. Now, I wanted to interject here. I'm recording from the future. I wanted to mention that when the exponent is all zeros, the exponent is going to be, well, you would think it's going to be 0 minus the bias, which is 127, and that would give us negative 127, right? But this is not correct, because the exponent, when the exponent is all zeros, this is used for both to indicate the zero numbers and for the normal numbers, right? So what we want to do in this case, that value is not used. This value is not used like this. When we have the normal numbers, the denormal representation. What we want to do is we want to say 1 minus 127. That is usually what is done. So when you see the when you see all zeros, that means you should do 1 minus 127, which is negative 126. This is because, as I said, negative 127 is used for this value over here. When it's all zeros, it's also used to denote zeros. So it is used for both zeros and denormal numbers. That is why we cannot use that directly. We have to say 1 minus 127, and basically we're saying 1 minus the bias. Sign, exponent, and fraction. Now for the fraction, we can see it's just 1, 1. However, remember when it's denormalized, then the exponent is all zeros. There's an implicit 0 in front of the fraction, so that's what we get. And now what we know here is that we have, that's negative 0.11 times 2 to the power of 126. That is now, if we calculate it, we're going to get get our decimal value that is extremely small. All right, notice something interesting. If we were to say, let's represent this as a normalized value, so that would be 1.1 times 2 to the power of, well, since we moved it over, we're just going to say 127. So now notice that we are not able to actually show this and represent this using normalized floating point representation, because we don't actually have that range. We're going out of the range, and we wouldn't be able to show this using normalized numbers. All right, so I think that the most important thing is to focus on the first part of this video. The denormalized functions aren't that common in exams and tests. I don't think and if there are, it's going to be similar to this. And if you're careful, if you pay attention, you will notice that if the exponent is all zeros, then it is a denormalized representation. In that case, you have the exponent 1 minus 127. And this is pretty much it. And you can also realize that we weren't able to actually represent it as a normalized one, where we would have a 1 over there and we'd discard that 1. We'd say that it's implicit, it's implied that it's there, so don't write it. And yeah, pretty much that is all. I know this denormalized explanation is spotty because it's a little difficult to explain it due to the fact that these numbers are so small in decimal form that we wouldn't be able to really, it was just, for me, it was difficult to show. But I think with persistent practice, you will get the intuition if you play around with these numbers, and when you realize that we have this restriction, that there's this small range of things we can have as an exponent, so that's why we're not able to represent everything. All right, thank you for watching. I hope that was useful.